Okay, but just as review, most common ion, and in this class I abbreviate it as MCI just because it's a long term to write, so feel free to do that. If you write MCI, it will always be considered most common ion. And a most common ion is basically the ion an element wants to become. Okay, so most common ion is an ion that an element wants to become. And we learned about how to find the most common ion. There's a pattern. So if you have your periodic table from the beginning of the year, you should actually have it on the periodic table. But we talked about how everybody in this first column wants to become a +1 ion. So hydrogen wants to become H+, Li wants to be Li+, so on and so forth. Everybody in this column wants to be +2. This column is +3, -4, -3, -2, -1. And this column right here, they do not form ions. Okay, so if you want to jot that down on your periodic table, just so that you have it for your notes, feel free. Just take it past.
Can I leave my backpack over here?
Yeah, that's fine.
Thank you.
And then one last caveat to that rule is that this most common ion pattern works on this side up till gallium and iodine, and it kind of just ends right there. Okay, so everybody above this, so these three +3, these three -4, but underneath it, they don't follow that pattern. So just a quick heads up about that. And again, if you have your periodic table from the beginning of the year, you should already have this on it. Okay? So if I ever asked you what is nitrogen's most common ion, you would write that it is N3-. If I asked you what is bromine's most common ion, it is Br-, so on and so forth. Yeah, what's up?
Why do atoms form ions?
Yeah, so it's because these are metals down here, and metals always turn positive, and so this pattern doesn't fit with that. Yeah. We go a little more in depth why in AP chemistry, but for now, just know it's because of the types of elements they are. All right, one other thing you need to remember, and we mentioned it as well, but everybody in groups 3 through 12, there is no pattern for this section. These guys are called transition metals, and they can form multiple ions. I will not expect you to memorize them because there's a lot of possibilities that go beyond the scope of this class. But for example, Fe can form Fe+, it can be Fe2+, it can be Fe3+, but again, you don't need to know that. Just know that the transition metals in the middle, they can form multiple different types of ions. Okay, so if I asked you what is, I don't know, cobalt's most common ion, there is no most common ion. It forms multiple different ions. Okay. All right, so that's generally what most common ions are, and a little bit of review on how to find them. But today we're going to talk about why elements form most common ions. Okay, but any questions on the general concept? Okay, so let's talk about why they form most common ions. So I want you guys to take a second, and I want you to draw the shell model for 2 different elements. Okay, I want you to draw the shell model for beryllium, and I want you to find the shell or draw the shell model for fluorine. So take about 2-3 minutes. Let's kind of warm up, review from last class. Work with the person next to you to draw the shell model for beryllium and fluorine. Okay, you're gonna do 2 separate shell models. Take a second to do that. All right, so let's go over how to do the shell models. I'm gonna go through it really quick since we did it last class. But the shells, all right, the shells are gonna depend on what row the element is in. So Be is in the second row, so Be is gonna have 2 shells. Same thing with fluorine, second shell, or second row, so it's gonna have 2 shells, okay? All right, in terms of the electrons, we said we go inside shells and then we go out. First row has 2 boxes. So we got 2 electrons in that first shell, and Be is box number 2 in the second shell, so it's gonna have 2 in the second shell. So for a total of 4, which is the atomic number, okay? And then for fluorine, same thing, 2 in the first shell, but for this one, it's going to have 7 in the second shell, okay? And that gives you a grand total of 9, which is the atomic number, okay? Everybody good with that? Okay, so that's review from last time, but let's talk about why they want to form the most common ion. So why does Be want to become +2? Why does F want to become -1? Okay, the reason has to do with the valence shell out here. If you guys take a look at the second shell, okay, we said that the second shell is represented by the second row, right? So if you look at the second row, there are a total of 8 boxes, right? And that means the second shell can hold a total of 8 electrons max. So it has an 8 electron maximum capacity. Okay, so in the second shell, you can have a total of 8 electrons. But if you take a look at beryllium and fluorine, do they have a complete valence shell? No, right? This one only has 2, even though it can hold 8. This one has 7, even though it can hold 8. And so if you look, they have incomplete valence shells. And the thing about these incomplete valence shells is that it makes the atom unstable. So the reason why elements become their most common ions is because if they want to have complete valence shells. Okay, so atoms, they want complete valence shells. Oh my goodness. Okay, they want to have complete valence shells. Okay, and so what they're going to do is they're either going to gain or lose electrons to have a complete outer shell, which is the reason why they become ions. They become positive or they become negative. Okay, so they want to make a complete valence shell. So let's start with fluorine. We said that fluorine wants to become -1. And the reason it wants to become -1 is because if you look, it currently has 7 valence electrons, right? So it's going to gain 1. So fluorine is going to gain 1 electron.
What is that?
The outside shell. 1, 2, 3, 4, 5, 6, 7. Yeah. So the valence shell has 7. So it's going to gain 1. If you gain an electron, you become -1, right? So F becomes F minus. And if you look now, it has a complete valence shell. And now it is stable. So that's how elements stabilize themselves. It's by gaining or losing electrons to have a complete outer shell. So F becomes F minus because it wants to gain an electron to become stable. Okay. All right, so that is what happens. So if you want to make a note on your paper somewhere, these elements right here, they want to become anions. They become anions by gaining electrons. Okay, but let's talk about these cations right here. So if you look at Be, it has 2 electrons in its outer shell, right? So in order to fill it up, you would have to gain 6 electrons, right, by gaining it. But the thing is, it's actually a lot easier for Be to just lose its electrons, because instead of, it could either gain 6 or it can just lose 2, because if you lose 2, that means, we talked about this last class, but if you lose your electrons, you lose your outer shell, and the inside shell becomes the new valence shell, and it is now stable. So Be wants to lose 2 electrons to become Be2+. And this is another way that it can stabilize its outside shell. By getting rid of its outside shell, the inside becomes a new outside and is already full. Okay, so cations, they become their ions by losing. And they lose a shell in the process. Okay, so this is the shell model for Be's MCI and F's MCI. Okay. And so on your assignment today, that's one of the things that you'll be doing. You'll be figuring out what the shell models for different most common ions are going to be. So hopefully not too bad. All right, any questions on drawing the shell models? It's kind of just a continuation of what we did last time. And now what we're going to do is we're going to add on a little bit to this. Okay, so let's move on to the next topic. So to do the next topic, we're actually going to be looking at shell models again. So I want you guys to take a minute. I want you to draw the most common ion the shell model for nitrogen. So take a minute, draw the shell model for regular nitrogen. So regular nitrogen. All right, guys, so I drew the picture of nitrogen up there for you, but nitrogen's going to have 2 in the first shell, 5 in the second shell. Okay, hopefully that's not too bad. All right, so one of the things that I often get asked is that we know that the middle of the atom, this nucleus, we know that there's protons in there, right? So the nucleus is positively charged and electrons are negatively charged. What we know from our knowledge of like magnets and what we've been talking about early in the year, that positive and negative, they start getting attracted to each other and they come closer, right? So if you have a magnet with a positive side, negative side, they come closer. Okay, so a question I get asked often is how come the electrons don't just all go towards the protons? How come they fly around? And the reason why they fly around is because the electrons, they are all negative, and we know that negatives, they push each other away. So there's this kind of balance of attraction to the nucleus and repulsion from the other electrons. And there's a way of measuring that, and we call that, it's kind of a long term, it's called effective nuclear charge. Okay, so take a second to write that down on your notes. Okay, effective nuclear charge. Okay, and the definition is pretty simple. It's basically how much an electron is connected to the atom. Okay, so effective nuclear charge is how much the electron is connected to the atom. And it depends on how much the nucleus, the protons, pull the electrons in, but also how much the electrons push each other away. Okay, and so what we're going to do is we're going to learn how to calculate the effective nuclear charge. And there is actually a simpler term that we use to write it. So I'm going to be referring to this as Zeff. It's Z and then effective. But I just call it Zeff because it's a lot easier. So if you ever want to just talk about this, you can always just say Zeff. Okay, and so the bigger the Zeff number is, we're going to do a calculation for it, the more tightly it's held by the electron. So if you have a Zeff number of 100, that's going to be holding the electron tighter than if you had a Zeff number of like 3. Okay, so bigger number means more tightly held. All right, so the formula for Zeff is pretty simple. It's going to be Zeff is equal to, okay, the number of protons. Okay, so it's going to be protons. And then it's going to be minus non-valence electrons. Okay, so non-valence electrons. Okay, so basically any electron that is not in the outside shell, that's going to be considered a non-valence electron. All right, so we'll use nitrogen as our first example. We're going to calculate the Zeff experienced by one of these outside electrons for nitrogen. And to do that, we just plug it into this formula. Okay, so if we look at nitrogen, how many protons does nitrogen have? 7, yeah, it's just the atomic number. So the first thing you're going to do is 7 minus, we look at the non-valence electrons, so the not outside ones. How many electrons does nitrogen have in the non-valence shells? 2, yeah, it's just going to be these two. So 7 minus 2, very easy calculation. It is 5. Okay, so the Zeff experienced by these valence electrons in nitrogen is just going to be the number 5. That's the, I guess, like the strength. Okay. All right, pretty easy. Okay, I'm gonna have you guys try a couple on you, or I'm gonna have you guys try 2 on your own. The first one will be kind of similar to this, but second one, we're going to combine it with the most common ion thing, okay? So let's, I'll put the formula back up, but I want you guys to take a second. Next example, I want you guys to calculate the Zeff, okay, for, let's do aluminum, okay, aluminum's valence electrons, so Al right here. And then I want you guys to calculate the Zeff, okay, for aluminum's most common ion. So you need to figure out what aluminum wants to be, and that's going to change up how many inner electrons there are. So take about 2-3 minutes to do that, and then after that we'll go over it, and then we'll move on to the last topic for today. Alrighty guys, let's go over this. I've heard some correct answers, some incorrect answers, but I love the conversation. Looks like you guys are kind of going the general correct direction regardless. But to make it easier to visualize, I drew the shell models for both aluminum and its most common ion. You don't have to do it for your assignment today. So if I ask you to calculate Zeff, you don't need to draw for all the elements if you can just do it without it, okay? But let's do the Zeff for a regular aluminum because it's a little bit easier. So if you take a look at regular aluminum, how many protons does it have? 13, yes, just the number on top of the box, so 13 protons. And you're gonna subtract the non-valence electrons. Remember, valence is only the ones on the outside. So it has a total of 3 on the outside. And then the inside there are total of 10 electrons. So there's gonna be 10 electrons. So aluminum is gonna have a Zeff of positive 3. Okay? So that kind of tells you the attraction between them. Alright, make sense? Okay, that one's pretty easy, right? The most common ion is where it kind of trips you up a little bit because your numbers are gonna change. So let's take a look at Al3+. Since it is still aluminum, the protons do not change. So it's still gonna be Zeff equals 13 minus, but we gotta look at what happens when you turn into a most common ion. If you turn into a most common ion, you lose the electrons in the outer shell. So you lose 3 because it's Al3+. And if you lose the 3 on the outer shell, that outer shell is going to disappear. So aluminum's most common ion only has 2 shells, which means this shell right here with the 8 electrons is the valence electrons. That means there's only 2 non-valence. So it'll be 13 minus 2, and then the Zeff will be plus 11. Okay. All right, so just to reiterate, again, aluminum, it loses electrons, right? So it becomes plus 3. If you lose the 3 right here on the outside, here, I'll erase it on this picture. If you lose the 3 here, you lose the outside shell completely. That means this second shell, which used to be an inside shell, is now the new valence shell. And so that's what we have to omit that from our calculation. So there's only 1 inside shell for Al3+, even though regular aluminum had 3 shells, okay? So that's the difference between the two. So this unit, we're talking pretty much about the properties that elements have. And the next property we're going to talk about is electronegativity. If you want to abbreviate it as EN, go ahead and do so. I always abbreviate it EN just because it's a long term. But electronegativity, pretty easy concept. It's how tightly an element holds on to its electrons. It has to do with Zeff. It's pretty much the same thing. But it's a fast way of comparing them on the periodic table. So electronegativity, it is how tightly an element holds on to its electrons. All right, and there are 3 things that matter when it comes to electronegativity, and these are actually in order of importance. Okay, so the most important thing is its most common ion. Does it want to gain electrons or does it want to lose electrons, right? Because if an element wants to gain more electrons, it's gonna hold the electrons that it has more tightly. So if it wants to gain electrons, it's gonna have a higher electronegativity. Okay, so if it wants to gain electrons, it's going to increase the electronegativity. But if its most common ion wants to lose electrons, it's gonna drop electronegativity. Because if you want to get rid of your electrons, you're not gonna be holding on to them very tightly. You're just gonna be giving them away. Okay, so if an element wants to gain electrons, it's gonna increase the electronegativity. If you want to lose electrons, it's going to decrease the electronegativity. All right, second important thing are the number of shells because it tells you the distance from the positive charge in the nucleus. Okay, and this is kind of self-explanatory. If it has more shells, okay, it's gonna be further from the nucleus, right? So do you think it's gonna be easier to take it away or harder to take it away? if it's farther away. So let's say this phone is my electron. If it's far away from me, do you think it's easier to take that phone from me or harder? It's easier because further away, right? I'm not holding on to it as tightly. But if I had the phone like right here, super close to me, it's harder to take the phone away from me, right? So same thing with the electrons. If there are more shells, it's further away. So that means it's easier, which means it's going to decrease the electronegativity. Okay, so more shells means lower electronegativity. Okay, and vice versa, obviously true as well. Less shells means it's closer, so stronger electronegativity. And then the last one is protons. And for the protons, the more protons there are, the more positive energy there is. So the higher the atomic number, the more protons there are, it's going to mean it has a higher electronegativity because it's a stronger magnet in the middle of the element. All right, so we'll do one example together, and I'll have you guys try two on your own, and then I'm going to show you guys kind of an easier pattern to use, and then we'll do one last one when we're almost done. Okay, so let's start with this comparison right here. We're going to compare sodium and lithium. So I want you guys to go to your periodic table. We're going to look at sodium and lithium. Okay, and we're going to look at which one is more electronegative. Okay, so we're going to look at sodium and lithium. All right, if you look at these two, does lithium want to gain or lose electrons? It wants to not gain, lose, because it's +1. So lithium wants to lose. What does sodium want to do? They both want to lose electrons, so we cannot use that as our metric. Okay, so now that we know they both want to lose, we're going to figure out the shells. If you look at lithium, how many shells does lithium have? 2 shells. How many electrons, or sorry, how many shells does sodium have? 3 shells. Okay, so now we have our difference, so we can figure out which one is more electronegative. Okay, so if you have less shells, is it easier to take electrons or harder? It is harder to take electrons because it's closer. Okay, so it's harder to take. And if it is harder to take, it means that it is more electronegative. Okay, so that means that between the two, lithium is more electronegative than sodium. Okay, and that would be the reason why. It's because it has 2 shells versus the 3 shells. And that's kind of the thought process that you want to go through. First, look at if it wants to gain or lose. If it's the same, then you move on to the shells. Okay, and then you move on to the protons if the shells are the same. All right, let's have you guys try 2 on your own, and then we'll move on to the last thing for today. Not lose. Fluorine's most common ion on the periodic table is -1. Beryllium is +2. So fluorine actually wants to gain electrons, and beryllium wants to lose. If something wants to gain electrons, it's going to hold the ones that it has more tightly. So fluorine is going to be more electronegative. So fluorine is more electronegative because it wants to gain electrons. Okay, so I know it's a little counterintuitive. I know minus means gain, plus means lose, but just keep that in mind. Electrons are negative things. So if you get more negative things, you become more negative. If you lose negative things, you become positive. All right, next one is nitrogen and sulfur. And so for this one, they both want to gain electrons. And so we got to move on to the shells. If you look at nitrogen, how many shells does it have? 2, yeah. Nitrogen is in the second row. How many does sulfur have? 3. So which one is more electronegative? Nitrogen is more electronegative. Same reason, it has fewer shells. Thank you for your courage. All right, now, I want to make your life a little bit easier. So there is a pattern, there is a trend for electronegativity, and some of you guys might have noticed it, but when you look at the periodic table, as you go up on the periodic table, you'll notice that you get less shells, right? There are fewer shells as you go up because higher means fewer shells. So as you go up on the periodic table, there are fewer shells. And as you go to the right, you will notice two things, is that the elements on the right, they want to gain electrons, right? And the ones on the left want to lose electrons. In addition, as you go right on the periodic table, there are more protons. Okay, which means that as you go up and to the right, that's kind of a pattern you can use to figure out which element is more electronegative. Okay, so if you guys notice on the ones that we've been doing, you'll see this pattern. The elements that are higher and to the right, they are more electronegative. So you don't need to do this whole process if you use this trend. It makes it a lot more easy, faster. Okay, I think that's also one of the questions on your assignment. So there's your answer. That's your trend. All right. Last thing that we're going to do is last problem, and this is going to be the final type of problem on your assignment, and you will have a question like this on your test, so I wanted to go over it. Yeah. The trend is as you go up and to the right, they become more electronegative. Yeah. All right, so last question, and the one that type of question you're going to have on your test is you're going to be given multiple elements, and you need to put them in order from least to most electronegative. Okay, so here are the 5 for this one. This will be our final example. Yeah. So go ahead and see if you guys can use your periodic table. I would recommend using the trend first because the trend helps a lot with getting it done faster. But I want you guys to organize these 5 from least, so least electronegative to greatest in electronegativity. So take about 3 minutes. We'll go over that and we'll be done. Okay, so for organizing it, we're looking at Y, we're looking at P, N, Cl, and F. Okay, so based on our pattern, which one is the least electronegative? Yeah, Y. It's on the most down, most to the left. So Y is the least electronegative. Okay, which one is the most electronegative? Yeah, F, because it's on the top right. So F is the most electronegative. So we can kind of cancel these out and everything else will go in the middle. Okay, next one. Which one of these 3 is the least electronegative? Yeah, P, because it's still on the bottom left for this group. So Y, and then P. And then we got N and Cl, which is kind of hard to tell now, right? Because they're kind of close. Doesn't matter which one's higher, which one's to the right. So we're going to use our information, the process that we talked about before to compare them. So for N, how many shells does N have? 2. How many shells does Cl have? Yeah, 3 shells. Which one is more electronegative? N. So it'll be Cl, then N. And that will be your order from least to greatest. If you got that, this type of problem on the test should be easy peasy for you.